Yeah, so to make it interesting, I never looked at this problem before now. So we have a similar starting point for the problem, okay? So a
Uh,
rectangular sheet of paper is folded so that one
yeah,
corner lies on top of the corner diagonally opposite.
yeah. But like that's
What
like
does that mean?
I got a rectangular sheet and I folded it like that and I counted our five sides.
Uh-huh. Okay. What does that mean though? Okay, can you someone explain to me what that means? They have a rectangular sheet of paper, yeah?
Or you fold it from one corner to the other. Like that's opposite.
So one
Diagonally
corner
opposite.
lies on top of the corner diagonally opposite. So this corner, yeah,
Yeah.
lies here.
Yeah.
Is that what we're doing?
Yeah. Yeah.
Okay, yeah. Okay. The resulting shape is a pentagon. Oh, is it a pentagon?
Yeah, I folded it and I counted five sides, which is a pentagon.
Oh, okay, good. Okay. Yeah, so this is the first step. We're trying to understand the problem. Yeah.
Yeah.
Okay, now we got some condition. The resulting shape is a pentagon whose area is 20% one sheet thick and 80% two sheets thick. I guess that makes sense, yeah?
Yeah.
So some of it's like folded on top of some paper and some of it's not on top of anything,
Yeah.
right?
Yeah.
Okay. Determine the ratio of the two sides of the original sheet of paper. So the length to the width, yeah?
Yeah.
So if this was like the width, this was the length.
Yeah.
We want like the ratio
Yeah. Of them.
length over width, yeah?
Yeah. Yeah.
Hmm. Yeah, I think this is a good, nice little problem for us because it's geometry, but it's like it doesn't really need any special things in geometry. You know what I'm
Yeah.
saying? So
Okay.
this is like, you know, this could be an AIMO problem, like one of the maybe middle to later ones. You know.
Yeah.
So I guess a lot of you have all got pieces of paper and try to fold them. Yeah.
Yeah. That's what I'm doing.
Yeah, that's a good start, I guess. So it's geometry, there's a lot of experimenting. So this folding the paper might be like akin to drawing a diagram.
Yeah.
Okay, has anyone noticed anything about the folding?
Are the foldings a pentagon?
Yes, okay. Well, anything about actually folding the you all folded the paper, right?
Yeah,
Do you
I
notice
folded it.
anything?
Oh no, I don't really like. I see like there's like some of the sheets are like hanging out outside, like it's not on top of another sheet of paper.
Hmm. Okay. What about Sunny? What do you notice anything about folding the paper?
Like it's two
Two triangles in a front, right? Oh, okay. So there's kind of like a symmetry, right? Is that what you're saying? So like when you fold it, like the two flaps which are only one single side of paper, one sheet of paper is really like 10%, 10%, and they're symmetrical, right?
Yeah,
You notice that?
yeah. I think about it now. I see it.
Okay. Joshua, do you notice anything
um
when you fold the paper?
when you fold it, the shape is the one the one layer thing is also on the other side.
Yeah.
I don't know.
Okay. I mean, you could say stuff like it's a right angle triangle. Yeah.
Yeah.
Um. Okay. So one thing I guess you could notice is look if you look at the piece of paper, right? Your piece
Yeah,
of paper.
yeah,
There's just like a glaring. There's like a literally a huge glaring fold line, right? You see what I'm saying?
yeah,
There's like a line that kind of goes like this, right? That folds across this line, yeah? And the triangles, I guess, how are the triangles related to this line? Well, it's the triangles, the line hits one of the vertices of the triangle, right? So like
yeah,
this is like one of the vertices of the triangle, and this is the other one, right?
yeah,
You know what I'm saying? Okay. Now that I guess I drew your attention to this line. Um, maybe I can also. Can you tell me more about this line and these triangles and stuff like this? And I guess this is the parallelogram that Sunny was talking about. It's like that, right?
yeah.
I'll give you a couple of minutes to think about it, but I want you to tell me what you notice about these lines.
Wait, there's 4 triangles, like there's 2 triangles on the outside and then 2 triangles inside the parallelogram.
Okay, yeah. Um, okay, but if you're gonna talk about the 4 triangles, what else could you say? So you have like
Triangles are like equilateral.
is that the right word? This is a 1 triangle, 2, 3, and there's 4 triangles, yeah? And so, for example, how are the triangles related to each other?
I'm not too sure.
I mean, they're not just 4 triangles in isolation, right?
Yeah, they all like basically all form a rectangle, I guess.
Yeah, but we said earlier, like triangles 1 and 4 were right angled, for example, right?
Yeah,
So they have some similarities with each other, yeah?
yeah.
Um, but can you describe in what way the 2 triangles are alike?
Like 2 and 3 are equilateral, like all the sides are equal and the angles are equal.
Are you sure they're equilateral?
Uh,
Or do they just look equilateral?
they just look like that.
Yeah, so just because they look like that doesn't mean they are like that, right?
Yeah.
But you know, it could spur on something to make you think that they're equilateral. Um, Sonny mentioned something about a parallelogram before, yeah?
Yeah.
What do you know about a parallelogram?
Like two sides are parallel.
You know anything else? So that's the definition of a parallelogram, yeah? The opposite
Yeah.
sides are parallel. But
Yeah.
what else do you know about them? Do you know anything about them?
Uh, Pretty sure like something about like the angles or something.
Yeah. Okay, so if you have a parallelogram, yeah, this all goes on to again. You have a parallelogram. You know the diagonals bisect
Yeah.
each other.
Yeah.
Do you know that?
Yeah. Yeah.
Do you guys know that? Okay, well maybe we can prove something like that afterwards. Um, okay, wait. So let me ask you. Do you know what like a relation? What could be a possible relationship between triangle 1 and 4?
Like basically whatever like whatever someone said, I forgot who, but like it's like right angled.
And so they're both right angled. We know that, right?
Yeah.
How do we know that?
Because you can see the 90 degrees. Like you can see there's 2 straight lines.
Yeah, because on a rectangle they're 90 degrees, right?
Yeah. Yeah.
But you also have in a parallelogram, like the opposite sides are equal, right?
Yeah.
Yes?
Yeah.
And so the opposite sides being equal is equivalent to being a parallelogram, right?
Yeah.
Yes?
Yeah.
So actually, the thing that Sonny saw that this is a parallelogram, right? You can actually
Yeah.
prove it, right?
Yeah. Because like you can
Because,
see.
well, at least you suspect it strongly to be true, right?
Yeah.
Because you have this side which is likely to be equal to this side by the symmetry, right?
Yeah.
You have that side that's likely to be equal to that side by the symmetry, right?
Yeah. Yeah.
Um, okay. Have you guys heard of this? The word congruent triangles. Have you heard of this? Have you?
Well,
Annie,
I've
have you
heard of
heard of?
it. I've heard of it, but I don't know what it is.
Okay, so basically, a congruent triangles is a way to say that, like, the relationship we have between 1 and 4, for example, and the relationship we have between 2 and 3. Okay, so you guys know the words, but we're gonna learn to use them. Okay, because basically the idea is, can you see triangle 1 and 4 basically the same? Yeah,
Yeah.
see what I'm saying? And triangle 2 and 3 are basically the same. Yeah,
Yeah.
and the way in which they're the same we call congruence. Okay, does that make sense?
Yeah.
So congruent triangles are triangles whose sides have the same length and whose angles are the same. Yeah,
Yeah.
you understand?
Yeah. I do.
Okay, so if the triangles have the same length, the angles are necessarily the same. Yeah.
Yeah.
So when you're showing triangles are congruent, you don't have to show all 6 things. Yeah.
Yeah.
Okay, but basically here we have two pairs of congruent triangles. Yeah.
Yeah.
So we have the two blue ones and the two right-angled ones. The
Yeah.
1 and 4 and 2 and 3. Okay.
Yeah.
But that might be a little bit of background because so the foundation of geometry, okay? So this is one of the 4 topics we have is so it's geometry, combinatorics, number theory, and algebra. Okay. So we're doing a
Yeah.
little bit of geometry and geometry, the foundations of geometry, especially the starting is the congruent triangles, okay? Because once you
Yeah.
have points and lines, you'll naturally get triangles. So triangles are essentially 3 points that don't line a line. Okay.
Yeah.
And to describe relationships with triangles, you have basically 2 things. You have congruence and similarity. Okay.
Yeah.
Similarity is is like congruence, but it's proportional instead of equal side lengths. Okay. So
Okay.
one triangle could be twice as long as the other one, if that makes sense.
Yeah.
So all the lengths could be doubled. Okay.
Okay.
But for similar triangles, the angles still have to be the same. Does that make sense?
Okay. Yeah.
Yeah, so we're not looking for words like equilateral right now. We're looking for words like congruent. So this triangle is congruent to this one. This triangle
Yeah.
is congruent to that one. Okay.
Yeah.
So can someone explain to me why 1 and 4 are congruent?
Because like they're both right angled and yeah.
Okay, so they're both right angled, yeah, and they both have one of the length. The long side here is all both the width of the rectangle, right?
Yeah.
So they're equal, right?
Yeah.
Okay, and then this one we don't quite know this one's equal, but we suspect it's equal by the symmetry, right?
Yeah.
And a triangle, if you know that's a right angle here, and you know this length and you know that length, there's no choice but to finish off the triangle like that, right?
Yeah.
So it's determined. And so the triangles, if the initial parts here are equal, then that's also
Yeah.
equal.
Yeah.
Okay. So what we have naturally like a few tests for congruence. So we have SAS, so that's the one we just did, side angle side. So if the angle's in between the two sides, that determines everything else. Yeah. And then we also said if the three sides were equal, the angles are also equal, so that's SSS.
Yeah. Okay.
Have you seen this before? You've
Oh
learned
no.
this at school. Some of you have learned this at school. Somewhere. You've learned this somewhere. Okay. And then there's only two other tests for congruence. So when you have two angles and one side are the same, then they're congruent. And if you have RHS, so RHS is basically if you have a right angle, hypotenuse, and a side. Do those words make sense?
Yeah. Yes.
Yeah. Do you mind if I call you Ani?
Sure.
Okay, so right angle, hypotenuse, side. So sometimes you don't, if it's a right angle, you don't actually need the included angle.
Yeah.
You just need any angle because by Pythagoras you know all three sides anyway, right? If you have two
Yeah.
sides. Okay. All right, does that make sense?
Yeah.
Okay, so this all comes under, so this is generally um understanding the problem, yeah? This is called understanding the problem. You take your time to understand the problem, okay?
Yeah.
Um, actually, a lot of problems are already solved in this phase, yeah?
Yeah.
The easier problems, once you understand them, you've essentially solved them, okay? And this problem, it's not um completely easy, but it's not that unlike the other problems. Um, it's a nice little problem if you think about it, right? Everyone can understand this problem. That's the
Yeah.
beauty of this. Okay. So what can we do from here? I mean, one other thing you can notice about this line, okay? Like this line is unique. Do you understand what I mean by that? This folding line is unique. Like if the line were to do something else, the the point would no longer fold.
Yeah.
Does that make sense?
Yeah.
Hmm. Actually, I might want to revisit also our need claim is it actually an equilateral triangle? Okay, because that's I feel like we weren't up to that idea yet, but now that I'm thinking about it, is it plausible that it's actually an equilateral triangle? So are two and three actually equilateral?
Maybe.
No.
Hmm. So if two and three are equilateral, then we have a rhombus on our hands, right? Do you know what a rhombus is?
Yeah. It's kind of like a diamond.
Yeah, so it's a parallelogram, but all four sides are equal, you know?
Yeah.
Mhm. Yeah, actually, all the properties of a parallelogram, like we prove with congruent triangles. Okay.
Yeah.
So, for example,
They're not equal. I'm sure.
are you sure?
I don't know this is something.
Well, how accurately were you measuring it?
Not really.
I mean, are they off by a lot or what?
Let's check.
Yeah, see, for example, like in a parallelogram, like we know these sides are like parallel, right? Yeah. Okay, and then somehow we can conclude that the opposite sides have the same length. Yeah. Okay,
Yeah.
so one way of showing that is you can show, if you look at this triangle here, right?
Yeah.
And then you can look at this triangle here. Yeah. Okay, and because they're parallel, okay, we know that this angle is equal to this angle, right?
Yeah.
Because it's alternate angles and parallel lines. You all learned this in year 7, right?
Yeah.
Okay, and then um, we have actually we can maybe break it up into these triangles, yeah?
It's off by like 3.5 centimeters.
Huh? So we have this angle is also equal to this angle, yeah?
Yeah.
Okay, and then so we basically have all three angles. If you have two angles equal, three angles are equal because it's it add up to 180, right? So we basically have two triangles where all the angles are equal, yeah? But can you see they also have a common side in the middle, so that side has to have the same length, yeah?
Yeah.
So then we have this AAS congruence, okay? That means these two triangles are congruent, okay? And once we know they're congruent, we can conclude the corresponding sides are equal. So the one opposite the dotted angle is this one, and that one, those lengths are equal now, yeah? And this one is opposite the circle, and this one's opposite the open circle. They're equal, see? So we're able to use the definition to prove that the opposite sides are equal. See that? And you can use similar arguments to prove all the properties. Okay. Have you seen those kind of proofs before? Yeah? Alright, just make sure if you know something or you don't know something, make it clearer to me, and then the more I know about you, the more efficient this will be, okay? Okay, so we're back to the question, are these triangles equilateral? And maybe like a broader question is like, what does it mean to fold? You know? What's the nature of that line? We know that line's unique, okay? It can't be any other line, but why is it unique? What's the relationship between the line and the points? Yeah? You'll notice maths is kind of about organizing things, okay? See, if you have four triangles and we have this relation of congruence, we only have two triangles to worry about, right? So organizing them by finding relationships between them. So we have essentially two triangles and we have a line, okay?
Yeah.
Yeah, so I think that question is a very good one about whether it's equilateral or not. Okay.
Okay.
So if you can answer me that question, I'll be very happy.
I think they are equilateral.
Okay, why?
Because like when you show like the diagram, like it showed that you had the AAS congruent, and then so I thought it was like equilateral.
Could you say that again?
Like when you drew the diagram, you said that it was like when you showed it said the AAS congruent triangles. So I thought it
Yeah.
would be equilateral.
Why would that be?
Because like you showed like that you have two angles that are equal and then like one side. So like if they're both the same, that means they have to be both equilateral.
Uh, so I mean, I showed that the side here
Yeah,
is equal to the opposite side. Yeah. I
yeah.
didn't show it's equal to the adjacent side. So
Oh, yeah. That means they're not equal.
well, they may be equal. Okay.
Yeah,
I didn't show they weren't equal. So this proves that in a parallelogram, the opposite sides are equal. Okay. But
yeah,
here we have a special parallelogram. Okay. And we want to know if it's actually a rhombus, basically. Yeah. Or
yeah,
even more than a rhombus because it's also equal to this length. Okay.
I don't think it's
Why do you say that?
um I don't know.
The thing I'm worried about is you're actually folding it and measuring it, but somehow your measurement, like what's your measurement? Are you just giving up on the measurement? So the measurement should give you two lengths, right? And the lengths, they're either going to be very close to being equal or they're not going to be very close to being equal, right? There are also some things you can notice without measuring, but I think measuring is not too bad at this point.
yeah.
Like, which lengths did you measure?
Um this and this.
Yeah, that's good.
Yeah.
So you could literally measure, like you measure this length, right? Because that's where you folded it. Yeah. Okay. And then you can measure. Let's see. You can measure this length. It's the distance between the fold and the corner, right? But I see quite a few crease marks in your sheet. Did you fold it across the right line? Okay, and then what were your measurements?
Um 22 and 25.
And you concluded they weren't equal. I'm not so sure about that. It's like pretty close. Do you have an extra ruler, Joshua? might be the ruler. Honey, have you measured the length?
Oh yeah, I'm measuring it right now.
Oh, that's a good question. Yeah, it may or may not depend on the sheet, right? So wait, do you think we could get lucky with A4 but not with like B5? But we still want to see if it's true. Okay. Yeah, of course. Alright, are we done measuring?
Yeah.
Do you have anything to say?
Like the fold line that I did is 17.5 centimeters. That's how much I wrote.
Hmm. I feel like I got like 26. Is that what you got? You got 25, right? So the fold line I got like 26. What did you say you got, Ani?
I got 17.5 centimeters.
17.5. Oh, you have some very small piece of paper.
Yeah. Yeah.
Okay, and then did you get something? 25.5. And then on the other side, what did you get? 23? 23, yeah? Okay. No, I guess, Joshua, I'm sorry I doubted you. I think you're right. Okay, so these two are different enough that we can say it's not equilateral, right?
Yeah.
But did we measure all three lengths or not? This one? No. So even though it's not equilateral, there's still a chance it's isosceles, right? Can we say if it's isosceles or not? Do you know what isosceles means?
Yeah. It means like two sides angles are equal and then the other one's not.
Yeah. Okay, good.
Isosceles is possible.
Yeah, so is it isosceles? Okay. So this is isosceles now literally means rhombus, okay? So whether or not it's isosceles, well, I mean it could be obviously it can't be equal to the 26, right? So it's basically where the blue are equal to each other. That makes sense? So the blue are equal to each other, then it's isosceles, and if it's isosceles, then the blue shape is a rhombus. Yeah?
Yeah.
Can that be true?
No, I think it's isosceles.
Oh,
Yeah.
Joshua thinks it's isosceles. And he was right before, so we should just believe him this time.
Yeah.
No, we have to verify, okay? Why would it be isosceles? Hmm? Okay, so if it is isosceles, or if you think it's isosceles, now the task is to understand why it's isosceles, or in other words, kind of like prove it's isosceles. Yeah. This is actually a really nice problem. It's actually very simple, but I think it's nice to try to understand it. See, the point of this is to like solve it gradually. Does that make sense? See, I could tell you the answer in one go, and you'll be like, "Oh, okay. Why didn't we think of that?" Yeah, but that's not really how you solve problems. You understand? It's not
Yeah.
about me showing you how smart I am. It's more about like piecing it together from nothing to the whole thing. Yeah. Yeah. So why might it be a sausage? Mm, what are you saying? You're saying how to find these lengths? Uh, the blue one and the which one? This one? Alright, which red one are we talking about? This one? This one? What about it? Find the ratio between the small one and like this blue length. That one? Okay. Oh, we can find that actually, yeah. So it's not along the lines of what we were talking about, but we can definitely find that, yes. Yeah. How do we find that? Wait, we're trying to you're saying find the ratio between like this length here and this length here, is that what you're saying? Are you still trying to show it's isosceles or is it something else? Yeah, so we can definitely find something else out about that. But before we go on to that, can someone tell me, does anyone know why it's isosceles? You know why it's isosceles?
Um,
Ani, do you know why it's isosceles?
Because two of the angles are equal and the other one's not. Because like that line in the middle that you showed is not equal, but then the other two ones are equal.
Uh, this is some very simple reason they're isosceles, okay?
Okay.
Look at your piece of paper. Yeah, so in the next 5 minutes, I want a simple reason why it's isosceles, okay?
Okay.
And the good thing about a simple reason is it's very convincing. No one has to get confused.
Yeah.
oh,
You found it?
because 1 and 4 equal.
Hmm.
And then the two sides are basically the longest side of the triangle, 1 and 4.
Yeah. Okay, so he didn't quite manage to turn it into words, but I think what he's saying is that this is the longest side of the triangle, yeah? Yeah. Can you see when that folds, it folds into this side here, right? When you fold it. So those sides actually equal. Does that make sense?
Yeah.
So when you fold it, this side goes to that side, so they're equal. And it's the same for the other side, okay?
Okay.
So this side here folds to this side.
Yeah.
Does that make sense?
Yeah.
And so if it was a parallelogram, then now it's a rhombus, okay?
Yeah. Okay.
Okay, good. So it's not necessarily equilateral, and we know it's, in this case, for A4 paper at least, it's definitely not equilateral, yeah? And so
Yeah.
this is where, like, Sonny was correct. Like, if it was equilateral, it could just be lucky, right? There might be
Yeah.
some paper that gives you equilateral, but we definitely know it's isosceles no matter what the paper, right?
Yeah.
Okay, so we know it's isosceles. So we actually know quite a lot about this, okay?
Yeah.
Um, yeah, so I don't want to get too off track, but mm, I don't know. So like usually what happens is if you keep going along this line, like naturally lead you to questions to ask, and you'll be easier. You keep answering, and you kind of steamroll until you know everything, right? But sometimes you might get stuck, and you want to take another approach, or you want to see something else. Um, so for example, Sunny was saying you can think about this length here. right? So that's something else we could also think about because what do we know about this length here, by the way? So so I'm not saying we're stuck because I think the other way of going we can still go a lot of further, yeah. But because Sonny mentioned this, we should probably have a look a little bit. So what do we know about like this length here?
Are they both equal?
Yes, but what else can we figure out about those lengths? So do you remember the actual question? This talks about 20% and 80%.
Yeah,
So don't forget the original question because that'll be definitely relevant to figure out those lengths.
yeah,
Right, do you understand what I'm saying?
yeah,
So I think sometimes if you understand what I'm saying, like you might be confused if you can't find the exact length, right?
yeah,
But I think we're not really after the exact length right now. We just want to know understand how the length related to the problem. Yeah.
yeah,
So for example, we know that the area is 20%. So you gotta be a bit careful here because you can't just say like because the area of these two triangles is just length times width, right?
yeah,
And that's 20% of the area of the one of the pentagon, right?
yeah,
So if it was 20% of the area of the rectangle, then you actually know that this is like 20% of the length of the rectangle, right?
yeah,
Which basically tells you a lot, yeah?
yeah,
Okay. And then you know that's 80%. But it's not the rectangle, it's the pentagon, right?
yeah,
So, but it's not that different, because if you have a relationship between the area of the pentagon and the area of the rectangle, then you just as well get this length as well. Yeah?
yeah,
That makes so so actually what you notice is you can actually just find this length if you know enough information about the shape. Yeah?
yeah,
Okay. Okay, but we're on the moment we were actually on the precipice of a major realization, so I was kind of reluctant to take a detour, but maybe this also uh, so if we get back to the equilateral isosceles triangles, yeah?
yeah.
Okay, what now if we assume it's isosceles, okay, what can we get from that?
Or we can get like that two sides are equal, and then we can figure out the other sides.
Mm, I want you to actually do something. So it's kind of and that's more of a tautology what you said. So uh, we have that these two sides are equal. Yeah.
Yeah,
there's some very interesting things we can figure out. So let me just remind you. So you know how I said the diagonals of a parallelogram bisect each other, yeah?
Yeah.
Let me just remind you how that's proved. Okay, so you have a parallelogram, right? And I've already proved that the sides are equal, yeah? So these sides are equal, yeah?
Yeah.
Okay. And I already proved these angles are equal. So these angles are equal, yeah?
Yeah.
And see, this angle is also equal to this angle, yeah?
Yeah.
That means the two blue triangles are congruent, yeah?
Oh, yeah.
And this is again angle side, okay?
Yeah.
And if the triangles are congruent, then the sides are equal as well, okay? So this
Okay.
side here is opposite this angle, so uh, it's equal to so it's opposite this angle, so it's this equal to this side, yeah?
Yeah.
And this side here is opposite the dot, which is equal to this side here, right?
Yeah.
So the diagonals actually bisect each other, yeah?
Yeah.
How is that related to our isosceles triangles? Like what happens if I draw, I mean this is a pivotal little joining, because this is where the 2 points are actually folding, right?
Yeah.
What if I draw that line? What can you tell me about that line? Let me erase some unnecessary information then. What do you notice about that line?
That line bisects the other line.
Okay, very good. So this line bisects that line, yeah?
Yeah.
We know like these lengths are all the same, right?
Yeah.
So like if you have an isosceles triangle, right?
Yeah.
Can you draw it to the midpoint down here, yeah?
Yeah.
What can you tell me about this line?
It cuts it like into symmetrical parts.
It's a line of symmetry, right?
Yeah.
Okay, and what do you know about the line of symmetry? What else do you know about it?
Uh, that it cuts the two triangles in, and then like the two triangles become right angle triangles.
Yeah, they're 90 degrees, yeah?
Yeah.
So this line is an altitude, yeah? Does
Yeah.
that make sense? And the way it's proved, see, if you look at the proof, it's like sides are equal, yeah?
Yeah.
Sides are equal,
Yeah.
and there's a common side, yeah? And this is SSS. That makes sense? So that
Yeah.
means these two angles are equal, but they also add up to 180, right?
Yeah.
They're they're on a straight line.
Yeah.
So if they're equal and add up to 180, they gotta both be 90, yeah?
Yeah.
Okay. So these angles are actually right angles. I don't know. Have you heard of the diagonals of a kite are at 90 degrees to each other? Have you
Uh,
heard of that?
no. No.
You've never heard of that?
Never.
Oh, okay. Well, I won't be able to use that as a sign of familiarity,
But I
but
might learn it later in school, but like I haven't learned it like right now, so I don't know what that is.
oh, well, you just learned it right now. So,
Yeah.
do you know what a kite is?
Yeah.
Okay. Well, this is a kite, right?
Oh yeah, yeah.
So we basically proved it, but you don't need that these two things are equal for a kite. You just need those two are equal. Yeah.
Yeah.
Okay. You guys know what a kite is? You've heard that the diagonals intersect at 90 degrees. Well, that's also what's happening here, right? Okay. Okay. And what else do we need to? What else can we mark in here? There's only one thing we haven't really marked in that's relevant to the stuff that we've been discussing. Something really obvious, not something terribly deep, but just like what else is true? Open the door quieter. Yes, I'm just asking something basic. So can you see that these lines are also equal in length, right? Does
Yeah.
that make sense?
Yeah.
So that's all like. So now we put like that's obvious. We know that, right?
Yeah.
Okay. But what I want you to see, can you see like once we put all this onto the diagram, okay? Can you
Okay.
see that we actually can understand completely what it means to fold along that line? So that's what I want you to think about for the next few minutes. So I think we're in a position to understand the problem completely now, okay? So especially like so the most mysterious part of the problem is what happening across the line, right?
Yeah.
I think now we have enough information to know exactly what's happening across the line, especially with regard to the 2 points. Okay, so they're
Yeah.
obviously being folded to each other, yeah. But what does that
Yeah.
mean, right?
Okay.
This 4.4. This is impossible. I told him to close the door quietly.
Inquiry.
It wasn't quiet.
Questions where you can just try every single number to 100 and then get that answer.
Oh, he's not talking about that question for. Yeah. So what does it mean to fold along that line? Okay. Yeah. So it's like a unique line. What is that line? Yeah. I'll give you 2 more minutes. Okay, so I don't think you actually need to know this terminology to solve the problem, okay? But I think we want to learn something, um, good takeaway from this. It's funny, like, understanding the problem is kind of like theory building. We're trying to build in the theory of the problem. So, have you guys heard of this thing called perpendicular bisector? Have you heard of that thing? Huh? So,
No.
so basically, a perpendicular bisector, it's literally what the name says, okay? So, if you have 2 points, okay, yeah, and you join them, there's a line that's perpendicular the, and bisects, yeah, the interval. This is called the perpendicular bisector. Yeah, does that make sense? So what a perpendicular bisector is literally all the points which are the same distance from these 2 points. Okay, and they form a line right down the middle. Okay, that's a very fundamental piece of geometry. And so what we've just understood essentially is that the fold line, there can only be one fold line, right? Is the perpendicular bisector of the 2 points. Okay. And in that sense, if we know about perpendicular bisector, then that kind of proves there's only one fold line as well. Okay. Because there's only one perpendicular bisector. All right. um, and that really makes sense. Okay. If you think about what folding means, okay, this will actually explain to you what folding means. Because what are you really doing when you're folding a point, right? You're literally reflecting it across the line, right? That makes sense? So if you're reflecting it, the distance from the line should be equal to the distance on the other side, right? And it's a right angles because you're reflecting it like across the line, right? You're not reflecting it at a weird angle. That makes sense? So folding across the line is literally reflecting across the line. Okay? So that tells you a lot. Um, so for example, like this angle should be equal. We already know that. This angle should be equal to that one. When you reflect it, this length should end up like that. You know what I mean? Okay. So, some people say, well, this would be contributing to solving the problem, but I would say this is still understanding the problem. Okay. But the beauty of understanding the problem is the more you understand the problem, the easier it is to solve the problem once you're trying to cash out. Okay. So here we have a complete understanding of the problem. All right. So now the question is, how do we use our complete understanding to acquire the answer they're asking for? All right. Does that make sense? So we completely understand this problem now. Have you guys learned coordinate geometry at school?
No.
Like X, Y axis?
Oh,
Oh, yeah, I know what that is.
Yeah, and you got like the origin is like 0, 0, and you have like equations of straight lines and that kind of stuff.
I haven't done that, but I know what X and Y and stuff are.
Okay. So at this very point, like this problem would be super easy using coordinates right now because you know exactly where everything is. Okay.
Yeah.
So maybe that could be a good exercise for some people who know about coordinates. But we're not going to use coordinates right now because it's like the beginning there, yeah?
Yeah.
But this problem is essentially done with coordinates, um, if you know what the fold line is. Yeah.
Yeah.
Okay, so you could have done that at the start, and it would have looked really quick. But the point is, it avoided all the steps in figuring out that that was the fault line. Okay,
Yeah.
and I think you can get into a lot of trouble if sometimes you just state that that is the case, like it's the perpendicular bisector, and you don't explain it, and then it's like what do you call it? It's a claim without a proof. Okay.
Yeah.
So I guess once we write our solution, we might want to spend some time proving that it's the perpendicular bisector. Okay.
Yeah.
Okay, but now that we know it's the perpendicular bisector, essentially we know all these things are symmetric about the line, right? The fold is literally just reflecting it now. We know that. Okay.
Yeah.
Um, how can we solve the problem now? You know? Do you still remember what the problem is?
Yeah. Like there's about the ratio of the two sides of the original sheet of paper.
Yeah. Hmm? What is? Do you know how you would find the. Wait, what are you guys doing right now?
I'm just on the Zoom thing.
Hmm. So I guess you might want to recall that little aside that we had when you mentioned this length, right? I mean,
Yeah.
so I guess it suffices to find sort of the relationship between the area of the rectangle and the pentagon. You know?
Yeah.
Yeah, like how is the area of the rectangle related to the area of the pentagon? You know?
Because like we fold the rectangle into a pentagon.
Yeah, so what's the area of the pentagon?
Uh, I'm not too sure.
No, no, we can figure it out, yeah?
Yeah.
Just think about what we've done. What happens when you fold? Like, look at our diagram. How do we get the pentagon?
By folding like the corner to the other corner, like
Yeah,
diagonally.
so what's the area of the pentagon related to the areas of these things here? Okay, that's what I want to know.
Cause like kind of similar because when you fold it, like the area will change or it might be the same.
Mm, I want a proper answer. Okay, so I want something definitive. Okay,
Okay.
so now the area of a rectangle here, right?
Yeah.
And then we fold it and we get the area of a pentagon. Yeah?
Yeah.
What's the relationship between those two areas? Or what is a relationship between those two areas? Okay?
Okay.
An extra 80%. So something really obvious. Okay? I don't need the full answer at the start, but there's something really obvious. We know what the fold line does now. Yeah? We have four triangles. Yeah? So the area of the rectangle is the sum of the areas of the four triangles. Yes? That's
Yeah.
obvious. Okay, so I want what the relationship is for the pentagon. Yeah, exactly. Did you hear what Sonny said?
Oh
If you
no.
say it again louder. Okay, you didn't say it any louder than the first time. But what Sonny was saying is that the area of the pentagon is the same area as the rectangle, but minus this fat triangle, right?
Yeah. Oh yeah.
Yeah, because that gets folded up. That makes sense?
Yeah. Yeah.
You see what I'm getting at now?
Yeah. I understand now.
Okay. So we actually know a lot, okay? And what do we know about? Yeah, so the three triangles gives you the pentagon, the four triangles give you the rectangle. Yeah? Okay. Now
Yeah.
what else do we know based on the question about the area? Say it again. Okay, so you gotta be more specific because this is a time to be careful, okay? So this one is 80% and these two are 20% of what? Of the pentagon, okay? It makes a difference. So so these triangles are 20% of um the pentagon, and this is 80%. Yeah?
Yeah.
So what does that tell us? What does that tell us? So we all got something to think about right now, yeah? We're not just doing nothing. Alright, that's good. Come on. Technical difficulties. Yeah, I'm hoping, yeah, I don't have to say too much more, but yeah, let me know what you guys get. Oh, okay. You're not talking about that. Okay.
Oh, can I please go to the toilet?
And
Can I please go to the toilet?
有人说话。
Oh, what?
Can I please go to
Hello?
the toilet? Yeah, can I
Yeah,
please go
sure.
to thank you.
Yeah. Now, are you back?
Yeah, I'm back.
Okay, have you guys come up with something?
Oh, not really. I couldn't figure out what to do.
I might give you a little bit more time. I think this is something you should be able to do. So you got what we got so far, right?
Yeah,
So we got that this is the area of the pentagon, yeah?
yeah. Yeah, I figured out that part, but like I didn't figure out how to like find the rest of the stuff.
No, I know you said that. So,
Yeah,
and we know that these are 20% of the pentagon, yeah?
yeah,
This is 80%, yeah?
yeah.
So what does that mean?
That means like it adds up to 120%.
No, it doesn't. No, like it doesn't.
Right.
It adds up to 100% of the pentagon, right?
Yeah.
But
Oh wait,
it's
no,
not.
I did like 20 plus 20 is all. I mean like 100%.
I thought you were doing something pretty good. What were you doing? Hmm? Uh, I don't think you necessarily have to do that. Sometimes it's better if you don't know too much, because then you can't do anything except for the only thing. What about you, Joshua? Okay, maybe I think the problem is not how to get it. I think the problem is you're not looking for it. Okay, see, you know, what do you have here? You have literally six triangles, right? Yeah, but all four of these triangles here are congruent. Yeah, and that one is congruent to that one, right? So even by me saying that, like, can you see, like, I'm naturally trying to find relationships between the triangles, yeah? And the area consists of exactly two types of triangles, right? So it's that one and this one. Okay, think about the relationship between them, yeah? Like, what's the relationship between the big triangle and the edge triangle? What is the relationship between them? And it's a very basic relationship. I'm not asking you for anything crazy. So my question is, what is the relationship between this triangle, yeah, and this triangle? I'll cap this at 2 minutes, okay? What is a very basic relationship between those two triangles? Yes, they have a common length. But relevant to what we were talking about, like the pentagon and the rectangle, you know what I'm talking about? We're talking about like the 80% area, 20% area, the pentagon rectangles, yeah? In terms of that information, what's a very, very basic relationship between the areas of these two triangles? Yeah, that's along the right lines, yeah. But what is the actual relationship? Yeah, that's exactly what I'm looking for. Okay. Okay, so this is basically what Sunny is saying is right, okay, but you said the wrong numbers, okay? So like if this is 20%, okay, and this is 10%, right? This is 10%, right? And these are 80%, so this is 40%. This is 40%, right?
Yeah.
So what's the relationship between the two areas? So I deliberately didn't say areas because I wanted you to think about that's what we're looking for, right? If I said areas, I might give it away too much. So what's the relationship between the two areas? Yeah, one is 4 times the other one, right? Does that make sense?
Yeah.
So now we can forget about the pentagon now, right? So this is a pure simplification, do you understand? So then the information given to us by the pentagon thing is really just telling us this is like area, like this area of this is like A, right? And the area of this is like 4A. That makes sense?
Yeah.
Okay. And these are the same, right?
Yeah.
Okay, now what do we do? What to do now? Can you get the answer from here? So what do we got so far? Anything? So we'd originally wanted to find like this length, for example. Do we have that now? Like this is if this was width and this was length, right? Of the whole thing. Do we have this length? Huh? Say it was a ninth. Yeah, so there's 18 A's altogether, right? And 2 A's is a ninth of 18, right? And the width is the same, so it should be a ninth of the area, a ninth of the length. Yeah. This is a ninth one on. This is L on 9. Yeah. Hmm? Yeah, I guess just in case this comes up, do people all know how to use Pythagoras?
Oh yeah.
So, I mean, may or may not be necessary, but if a push comes to shove, this might be the last Pythagoras' theorem, yeah? If you have a right angled triangle, this C, and this is like A, this is B, yeah? And A squared plus B squared equals C squared. Actually, the converse is also true. If you have A squared plus B squared is C squared, then it's also a right angled triangle, right? Alright, what can we do from here? So you might want to notice that the areas are now pretty consistent if you just do some basic, like for example, if you do this area of this big triangle here, that's 8a, right? Which is 8 times little a, and so this length here should be 8 times the length of this, yeah? The height's the same, the height's the width, yeah?
Yeah.
Or like if you cut across this trapezium, it's half the area. Okay, so the areas are pretty consistent. Okay, we just want a relationship between L and W. Okay, so for example, this is L on 8L on 9, right? Yeah.
Yeah. Yeah.
What can we do here? Um, Alright, you have any ideas what to do?
Not really.
Okay, so remember we just need one relationship between L and W. Yeah. Can you
Yeah.
see where we might get that?
Um, maybe from like that one like side length, and then you try to figure out it. But I'm not too sure.
I mean, for example, we know that this is 8L on 9, right?
Yeah.
Yeah. You see that this is also 8L on 9 here.
Yeah, and then like
The
that's
same,
also
right?
the other one is also like the other two are also the same.
Yeah. But let's just focus on this, yeah?
Yeah.
You see how that gives you a relationship between L and W?
Yeah. Because like you can see that like L over 9 and AL over 9 like they form the width.
This is a right angle triangle, okay?
Yeah.
So Sonny said it, but not very loudly. It's Pythagoras, yeah?
Yeah.
See? That's very good. Alright, see if you can finish it off from here, okay? So I don't want to
Okay.
do stuff for you that you can do for yourself. But we're almost at the end, okay? So you're doing very well. So
Yep.
let's do it.
Alright, so like should I like solve the Pythagoras theorem thing?
Yeah, of course. And you can do it
Alright.
without us. Yeah.
Yeah.
So it is. Well, I didn't go into this knowing the answer, so if you're not
Yeah.
sure, then I'm not sure. You know,
Yeah.
we're as sure as the proof we used to get to. And in some sense, that's kind of like the mathematician's role to have the certainty, right? So Joshua, you know what we're doing? Are you doing it? You can do it on another piece of paper, yeah? There we go. 8L on 9 squared. Right? All right. Do you know how to finish it up from here? I'm pretty sure you
But
have it. Right, you.
yeah, I'm solving the thing. I'm solving the Pythagoras theorem right now.
The what?
Like the Pythagoras theorem thing. I'm doing that right now.
Okay. Pythagoras. Yeah. I'll give you one more minute. All right. You see what to do? Okay. What do you do? Let me know.
You. Okay.
Okay. What do I do?
You. Do the square.
Okay. And then what do you get?
64 L squared over 51 equals L squared over 18 W squared.
Yeah. So you don't actually have to square the nines. So at the moment, what you essentially have is you have 64, right? So it's really just it's 64, and then it's like L over 9 squared, right? Equals L over 9 squared plus W squared. You know? You don't need to square the 9. Okay. Um, Ani, have you done this? What do you do next?
Um, but I did it a different way, but I think like I did it a different way, but I think like this is like a different way. But I'll just like to listen to what you're doing.
Okay, yeah. Okay, so yeah, I think it's okay to have different ways, but in some situations, I think you have to be aware of what's most efficient. Yeah.
Yeah,
So if you're, yeah, so sometimes, yeah, so you got 63, right?
yeah,
63 L over 9 squared equals W squared. Yeah?
yeah.
Okay, then what did you do?
Oh, and then I put the square root of like the thing on the other side, like so W is equal to the square root of like 63 times L over 9 in brackets square.
Yeah, so you took the square root of both sides. Is that what you did?
Yeah,
So then W, and then so usually it's plus minus, but we know everything's positive. Yeah.
Yeah.
So that's something that's going to come back to haunt you if you don't take care of that.
Yep.
So you get root 63 L over 9. Yeah.
Yeah.
Okay, then what did you do?
Um, and then I did wait, and then I put it as 9, like square root of 9 times square root of 7 L over 9, like times L over 9.
Yep. Okay, that's good. The square root of 9 times the square root of 7 times L over 9. Yep.
Yeah, and then like I didn't know what to do after that though.
Oh, I mean, we're basically at the answer. So what's the question asking you, remember?
The ratio.
Yeah, so Joshua, what do you do from here, you know? I mean, one obvious thing is the square root of 9 is 3, right? So the square root of 9 is 3,
Yeah.
and the 3 cancels with this to get 3, right? That makes sense?
Yeah.
So then you can divide both sides by L or divide both sides by W. Um, and get root 7 over 3 equals W over L, right?
Yeah.
You understand? So you just divide L onto the bottom here.
Yeah.
Wait, your yes sounds a little bit. So you got root 7L over 3 equals W, right?
Yeah.
So another way of saying that is W is root 7 over 3 times L, right?
Yeah.
So let's say root 7 is like 2.6 or something, right?
Yeah.
Or maybe 2.7 just to make it easier for me. And then 2.7 divided by 3 is 0.9. So W is like 0.9 times L. So you know the relationship now, yeah?
Yeah.
So the ratio is, like it's 90%. W is 90% of L.
Yeah.
That makes sense?
Yeah.
These yeses don't sound as confident as I'm hoping for, but like we've solved the problem now. Yes?
Yeah. I understand now.
Okay, good. So the ratio from width to length is root 7 on 3.
Yeah. Okay.
Yeah, so root 7 is less than 3, yeah? We need that
Yeah.
for W needs to be less than L, yeah?
Yeah.
Okay. Yeah, so that's a complete problem. Well done. Okay, so in summary, I mean, obviously the problem like doesn't actually necessarily take this long. Once you get better at it, it's kind of you can probably get a lot of this right away. Yeah. But what I've kind of shown you is like a general process of investigating a problem. You understand? Like
Yeah.
most of the stuff you do at school and other people teach you, they're just kind of it's more just memorizing the solution. You know what I'm saying? But you
Yeah.
can't memorize a solution that you don't have. Okay, this is more like about creating the solution. Does that
Okay.
make sense?
Yeah.
So this process, it can solve very easy problems. It can solve, I guess this would be more like a easy medium problem, okay? But the same process can solve even unsolved problems in mathematics. Does that make sense?
Yeah.
It's not like it's not like the unsolved problems are any more like they might take longer to do, right? Or it might
Yeah.
take new ideas, observations along the way, but we're still investigating. You
Yeah.
understand?
Yeah. I understand.
Yeah. So this approach, you can use it to solve any problem. Yeah.
Yeah. Yeah.
And notice we didn't assume you knew anything, right? But we kind of there's some things we'd like to remember that we learned along the way to use next time. So like perpendicular bisector, isosceles, congruent, similar, those kind of things, they'll come up a lot. So we want to kind of, we want to not have to rediscover them every time. Yeah. So we
Yeah.
kind of try to memorize them. But at the start, it's the memory is not as good because at the start your mind is not as good, so you memorize things with low quality. Yeah,
Yeah.
okay, because you don't really understand them as well. But later on, when your mind gets better, you get more logical. You've had some more experience, and your brain literally grows. Okay,
Yeah.
the quality of your understanding and knowledge will also improve. Okay, and then you
Yeah.
can memorize
Okay.
things with more confidence.
Yeah.
Yeah. Okay, so if you look at the five problems, we have the first three, five, everything but problem four on video. Okay,
Okay.
so if you do them, you can try them at home, and we send the video. Okay.
Okay.
Okay. So have a good day. We're gonna go into our lunch break now.
Okay.
Do you have any questions?
No, not really.
Okay, you got stuff to do, right? Don't just do nothing. If you have time and you want to do maths, I'd suggest do like these problems or something. Yeah.
Yeah. Okay.
Okay, and then um, yeah. So if you do one, two, or five, I have them on video.
Yep.
All
Okay.
right.
Yeah.
All right.
Okay.
I'll see you tomorrow. Okay.
Yeah. See. You. Bye.
Bye.